Okay, so we have looked at ways to use our understanding of the first derivative and the second derivative to graph functions. Now we want to kind of expand on our understanding of the derivative and the second derivative and use the same idea, but instead look at applications, word problems that we can actually solve. But before we do that, I actually want to go back to something that you probably saw a long time ago, and we can actually see where it comes from now, and then we'll go from there. And what I mean is, way back in, it may have actually been in like pre-calc, high school, some math class, I'm not really sure. A lot of times you did something where you were given, some quadratic, 2x squared plus 6x plus 8. And I'm actually just going to make that right there, just to make the math a little bit easier in a second for this. And then you were told, there's a quadratic, find the vertex. Which we understand from a graphical perspective, whether my quadratic looks like this or this, we find the vertex, we find the max, we find the min. And if you remember when you took pre-calc, or whenever you might have seen this, there was a formula you always learn. I think you learn x equals negative b over 2a. And if you just pick, let's see, that's a, the coefficient here is a, that's b, and that's c. And if I find negative b over 2a, that will tell me the x value of my vertex. Then I can plug that x value in and I can get the y value. And you use that, again, from say a pre-calc perspective, to try to find the maximum value, the minimum value. Use it to graph, because if you find the vertex, that goes a long way towards figuring out what your graph of your parabola looks like. And again, you may solve basic optimization problems in pre-calc about finding a maximum or a minimum, finding a maximum cost, a minimum cost, things like that. And you just learn this formula and memorize it. And the question kind of becomes, where does it come from? So now, suppose we have a regular quadratic, standard form, no numbers, just letters. And now we say, find the maximum of that arbitrary quadratic. So find the vertex. Well, let's see, now I understand from the first derivative test that if I want to find a maximum, I just need to take the derivative and set the derivative equal to 0. The same holds true for a minimum, obviously. So if I want to find the maximum of this quadratic right here, take its derivative. Keep in mind here, a, b, and c are just constants with respect to the variable k. So here, if you bring down the 2, you get 2ax, plus here the coefficient of x is b. So there's my derivative. Now we say, using the first derivative test, set that equal to 0 to find the critical points. And then you solve for x. Subtract the b, divide the 2a. So I subtract the b, I divide the 2a, and I get x equals negative b over 2a, which is my critical point, which means it's the only place I can potentially have a maximum or a minimum. Here there's no way to tell because I don't know if a, b, and c are positive or negative. But the point is, this is a formula you memorize in pre-calc, and the reason you memorize it in pre-calc is because, bear with me a second, my cat's on the cat tower again, and she's looking like she's about to launch herself off of it, so this might shake in a second. Okay, we'll see how that goes. Stop eating the cat tower. Okay, and the point is, in pre-calc, you learn this formula because it's pre-calc, and you don't know what a derivative is, and you don't understand how they work. So they tell you, here's the thing, just trust us, it's correct. There's actually other algebraic ways to find this formula. Here, just using the idea of the derivative, we immediately see, oh, the maximum, just take the derivative, set it to 0, there we go. But what that means is, I can certainly find the maximum or minimum, there she goes, find the maximum or minimum of a quadratic, take the derivative, set to 0, and go. Which means those optimization problems that I solved in pre-calc, again, normally you would solve, say, cost problems, revenue problems, things like that. Well, now I can actually solve them using calculus methods. It's actually essentially the same method. And I will point out, as I pointed out before, it is completely okay to say, hey, here's a quadratic, use the formula, find the vertex, and good to go. Because you know it works, you did it in pre-calc. This just shows us that that idea you learn in pre-calc to solve one specific type of problem, the maximum of a quadratic, is actually solvable by using our understanding of the first derivative. It also means that now we can solve more complex problems, more complex optimization problems, using the same trick. Find a function, take its derivative, set the derivative to 0, and then we know according to the first derivative test, anything that gives me 0 has to be a max or a min, which is what I'm always looking for optimization problems. So, now we're going to start solving some, but we'll solve some that are different than the ones you used to from pre-calc. And I will also point out, there's a bunch of them in your book. I read through the section and I read through all the problems in there. But in order to give you as many examples as possible, I'm going to deliberately use different examples than the ones in your book, so you can see as many examples as possible worked out. So maybe, well, we'll start with a simple one. A lot of these optimization problems that we do in calculus end up being geometric in nature, much like the related rates problems that we do. But instead of doing a geometric one, we're going to do something slightly differently. So I want to, let's see. Find the maximum product of two numbers whose sum is 40. And I will stress right at the outset, the way we're going to go about setting these up and thinking about them is actually very similar to the related rates problems we've already done. Find a formula. In a lot of instances for this class, they'll end up being geometric formulas. The only difference is with related rates, you're talking about rates of change over time, the speed that something occurs. So you go with that related rates implicit differentiation trick. Here, as soon as you see find the maximum or find the minimum, it means you're doing optimization, but you end up doing the exact same thing. And the cat's probably going to jump back up here in a minute. We'll see. Okay? And then as soon as I want to maximize it, I do the same thing to start. First, I need an equation. Find the maximum product of two numbers. Okay, I have two numbers. Just get up there. Stop moving. Okay, good. Find the maximum product of two numbers. So I'll just say P for product is equal to x times y. Two numbers, x and y, whose sum is 40. So the sum of x and y is equal to 40. And now I end up with two equations. First, we say, what do I care about? If I care about the product, this is the equation I care about the most. So this is just something I'm going to use to help me solve the problem. And the problem, if you recall related rates problems, there's two variables in there, x and y. Now, since I'm not doing implicit differentiation, I am just taking a derivative here. I need that to be in terms of one variable. And keep in mind, that's not a function y now, that's a variable. Two numbers, x and y. So we're not doing implicit differentiation. I need a way to write that in terms of one variable. So I use the other equation. I'm just going to solve it. It doesn't matter which one I solve it for, so I'll just solve it for x. X equals 40 minus y. Now substitute that in over here. P is equal to x, which is 40 minus y, times y, which is 40y minus y squared. Now that's the equation for the product that I want to maximize. How do I maximize it? First derivative test. So I take the derivative. P prime is equal to, let's see, 40 minus 2y. Now I set my derivative equal to 0. 0 equals 40 minus 2y. Add the 2y. 2y equals 40. So y equals 20. One thing I would point out, if we were just, say, graphing this function to determine if it was a max or a min, the next step would be to do a sign chart, put 20 right there, and then check the values on either sides of this in the derivative, to see if you end up getting a positive or a negative to make sure this is the maximum. If we do that really quickly, here's my derivative right there. If I pick something to the left of 20, say 10, 2 times 10 is 20, 40 minus 20 is 20, that's positive. That's positive, so I'm increasing. If I pick something bigger than 20, say 30, 2 times 30 is 60, 40 minus 60 is negative 20, that's negative, so it's going down. Which means the function increases then decreases, so this is a maximum, which is what I was looking for. So that's the y that I actually care about. For these, you can do a sign chart every single time if you want to. If there's more than one critical point, you're going to have to get an idea of what's going on. But when I'm doing these, generally, I'm not going to do the sign chart because I know it's going to be a maximum or a minimum, whatever I'm looking for. But you can always do that to check to make sure it's right. And if you have more than one critical point, definitely check. Now, we get y equals 20 up here. X equals 40 minus 20, so x equals 20. Now I have my x and my y. Now answer the problem. Find the maximum product. Well, it's x times y. 20 times 20 is 400. And there's my maximum profit. All things being equal, I actually like these. As I mentioned before, when I was a student, I didn't really do well on the related rates and the optimization, the word problems. Now as an instructor, I really, really like them because they're a whole lot of fun. And from your perspective, as you maybe look ahead both to the next exam as well as the final exam, which is cumulative, there's really only 2 word problems that we solve in this class. Either related rates, take the derivative with respect to variable t, treat everything as a function, do a whole lot of chain rules. Or optimization, find the max or the min. Given that optimization problems have to tell you to maximize or minimize, it should be fairly straightforward when you see a bunch of word problems, which trick it is you're going to use. And then these are generally straightforward. Find a function that you're going to maximize, which you'll generally be given maximum of the product. So there's my product. If you end up having more than one variable, you won't always, but if you have more than one variable, find a way using the other information to create some equations, relations, so you can rewrite your equation in terms of one variable, right here, I guess. Then take the derivative, set it to 0, find critical numbers, and do everything we've already done with our first derivative test. This video is already approaching maximum length of time here. I'm going to do a lot more examples, but I'll put them on a separate video because this is already too long.